So let's go ahead and take a look at how we would do this in Excel. I went ahead and pulled up the Unit 2 workbook for the Baylor women's basketball stats, and when I created this binomial sheet, I intentionally set it up for you to be able to answer pretty much any question. So what I want you to do is go ahead and create a copy of this sheet, and there's two ways that you can do this. And what I would suggest, I'm going to go ahead and right click on the tab on the bottom, right click and do move or copy. And I'm going to say create a copy, and then to a book. I'm going to do a whole brand new book. Okay. And so it's going to open this up, and now I have 2-2-3 binomial. And so what I'm going to do is Binomial Calculator. Okay. And I could do all of this for you, or I could encourage you guys to do this yourself, but something that I've done in the past is basically have workbooks that are full of calculators and just shortcuts, things that I've set up in the past with formulas that when I put information into these calculators, it gives me the answers back. And so these don't actually have formulas in them, but you certainly have the ability to create the formulas so that way if you put information in here, it can just give you the information back. So when we're doing a binomial probability distribution, we have to go through this basically a 9-step process to get everything that we want. Now, do you have to go through the 9-step process if you just have a simple question? No. But we're going to go through this process. So first of all, let's get rid of the stuff that is unique to the binomial distribution question about Coach Mulkey and her team. So we're going to delete that, and then we are going to, what's the expected number? Okay. And let's just make it so that it's not Coach Mulkey's information. What's the probability of making exactly X number of successes, or of having exactly X number of successes? Okay, then next, what is the probability of having X or less number of successes? And so just keep on going all the way down, having X, and then let's go this one right here. Okay, so in this particular one, it's basically saying I want to be this percent confident that there will be less than a particular number of successes, and so XX, this percentage is the alpha level in the equation. So if you go over to the binomial inverse equation, that R right there is the percent of basically how confident you want it to be, and it's the term alpha, and we'll be dealing with that term a lot later. Let's do 8 period. Then for number 9, what's the probability that there will be between will be between 40 to 50 between let's see here, x1 to x2 number of successes. And so just go all the way down this list, and then we'll be able to answer these. Okay? So first of all, what is a success? A success in this situation is individuals typing less than 60 words per minute. And once again, successes are not necessarily something that you would deem as a success. Successes are whatever percentage that you are looking at in the equation, whatever that percentage reflects. So in this case, 25% represents the probability that an individual will type less than 60 words per minute. So the success is the that because it's associated with that 25%. Okay, the set number of trials, I said that there's a total of 34 people that we are observing. And then the needed number of successes, specifically there were 8 successes last time, so we need to decrease that number, so we need to get down to at least 7. And then the empirical probability, like I said, the probability of it is being 0.25. And then the mean or expected outcome, just do equals 0.25 multiplied by 34, and that gives us 8.5. 8.5, and so we're going to look at this right here, and you notice that the most probable outcome is 9. Most probable outcome is 9, and so what we need to do right here is actually round that up, because we are dealing with a discrete distribution. It needs to be rounded. So it either needs to be rounded up to 9 or down to 8, but it's very clear that it needs to be rounded up to 9 because it's 8.5, and let's see here. Yep, just straight up 8.5. So it's actually, we're just going to put 9. Okay. Then binom.dist. So this one right here, if I want to know what's the probability of exactly 7 successes, or exactly 7 individuals, well, actually, since the most likely outcome is 9, we can actually do 8. Okay, so 8 is what's needed, so I changed that to 8, and the reason why is because all that we've got to do is get below 9. And since 9 is the most likely outcome, or appears to be the what it was last time, we can go all the way down to 8. So equals binom.dist. Okay, then we're going to put the number of successes. So right here is 8. Then the number of trials, the total number of trials is 34. Then the probability of success at each trial is 0.25. And then cumulative, we want to say false. And the reason why is because cumulative gives us exactly 8 and only 8. So if you hover over 8, this is 0.1. Okay, if we want to know what the most likely outcome is, what we're going to do is just multiply the empirical probability by the number of trials. So we're going to do equals 0.25 multiplied by 34, which that's going to give us an 8.5. So 8.5, that's not going to be the most likely outcome. The reason why is because 8.5 is not possible. So because we're dealing with a discrete distribution, we need to make sure to have a whole number right there. So the question is what is the most likely outcome? And so we need to round this, but do we round it up? Do we round it down? What is it that we do? And so what we really should do is, let's see here, there's a couple options, but I'm going to show you right over here first. This is a chart, or a XY scatter plot. But the way that I use it is a visual of the binomial probability distribution. And if you hover over this dot right here, this right here is the most probable outcome. And that right there says number 8. Number 8. And so we're going to put number 8. 8 is the most likely outcome. Now, if you want to check between like 7, 8, and 9, you could do something like this. So equals binomial .dist, and then we can put the number of successes. So we're going to put number 8, and then we're going to put the number of trials, and so we're going to put 34 trials, and the probability of success at each trial, that is going to be 0.25. Okay, and then last but not least, we're going to put false, and the reason why is because for this particular instance we only want 8. Okay, so this gives us 0.156364. And then if you wanted to compare it to, let's say, 9, so we've got 8 right here, and so now we're going to compare it to 9. And so, let's see here, instead of 8, we're going to put 9. And 9 gives us 0.1505, and so you'll see this is a little bit less likely than this, and so you can just double check your work really quick and you can see that it is in fact the most probable outcome. Or you could just round it down. So, so in general, it's just safe to round it down. So if you got 8.5, round it down to 8. If you've got 7.5, round it down to 7. And so the mean or most probable whole outcome is going to be basically when you've got the whole number and the decimal, just round it down to find the most likely outcome. Now with the binomial distribution, like I said earlier, you can do 8 for being the the needed number of successes is going to be 7 because the most likely outcome is 8. And then to find this, we are going to find, okay, we need 7 outcomes, or we need 7 successes out of, this is supposed to say 34. 7 successes out of 34, and so the probability of exactly 7 successes out of 34 is going to be 0.138991. Okay, and then coming right here, the probability of less than 7, we just do the exact same thing, binomial distribution. This right here is the needed number of successes. So you put the needed number of successes, which tells you the number of successes or less, or the probability it adds up all of those. And then you multiply it by then the next one is the number of trials, then the probability of success at each trial, and last but not least, we're going to put true. And by doing true, what this does is this adds up the probability, let's see right here, that's 6. It adds up this probability with this one, with this one, with this one, and adds up all of these probabilities together to tell you the probability of 7 or less. Okay, so that's 35.7, or roughly 36% of the observations are going to be 7 or less. Okay. Next, with the binomial inverse, we've got equals binomial dot inverse, and what this does is we're going to put this information in and I'll show you. We've got the number, which is 34. Then we've got the probability of success, which is 0.25. And then we've got something called alpha. Alpha basically says we want to know how confident we are with what this is. And so if I say I want to have 0.99, which essentially means, which essentially means I want to be 99% confident that this number of observations or less, that these ones are going to be successes. So I want to be 99% confident that there's going to be 15 successes or less. Okay, or if I were to change it, instead of 299, I could change it to 90. Okay, I am 90% confident that it's going to be 12 or less. Okay, that it's going to be 12 or less. And so that is basically how that's set up. You put in the probability, hey, I want to be this percent confident that it's going to be this value or less. And last but not least, we've got the binomial.dist.range. And then we're going to put the number of trials, which is still going to be 34. Then the probability of success at each trial, which is 0.25. And then we've got the number of successes. The lower number of successes, let's just say 5. Well, the upper number of successes, let's put 10. And press enter, and then we can tell that 74% of the observations are between 5 and 10 inclusive. Going to your worksheet, though. Okay, let's pull up your worksheet. We've got the probability distribution worksheet. And so let's see here. Let's see if we can find one that's got a binomial probability distribution. Okay, let's see here. So a National Honor Society has an acceptance rate of 32%. A student either gets accepted or they do not. The probability of each student getting accepted is the same. This past year they had 100 applicants. So this right here is a binomial probability distribution because there are either two possible options, either success or failure. So either they get in or they do not get in. So what we're looking at is an acceptance rate of 34%. So what is a success? A success is someone gets admitted to an honor society. Okay, so the number of trials is 100. So we've got 100 right here. Okay, and then the needed number of successes. Okay, so we don't really have a needed number of successes right here. Let's see here. Oh, right here, 42. We want 42 is going to be the number of successes. The empirical probability is 32% or 0.32. And then the mean or expected value or outcome. So all that we've got to do is equals 32 or 0.32 multiplied by 100. And that gives us the most expected outcome is 32. And so the most expected outcome is 32 individuals getting accepted. So looking at this now, the binomial probability distribution, what is the probability of 42 students being accepted? In order to do this, we do equals binomial distribution, okay, the number of successes, which is 42, the number of trials, which is 100, and the probability of success at each trial, which is going to be 0.32, and then cumulative, and we're going to say false. Okay, and so the probability of success here is 0.008974. So it's a very minuscule, what's that called? Minuscule number. Now, if I were to say what is the probability of 42 or less, we can do the same thing. Equals binomial dot dist, and then put binomial.dist, and then we're going to put the number of successes, which is going to be 42, the number of trials, which is going to be 100, the probability of success, which is going to be 0.32, 0.32, and then we are going to put true to say we want 42 or less. So if I put false, it gives you just 42, the probability of exactly 42. If you put true, it gives you 42 or less. We're going to put enter. And so we can tell by this that 98%, 98.64% is the probability that 42 or less students will get accepted. And then once again with the binom.inverse, the inverse binomial probability, we are going to do equals binom.inv, and then we're going to put n, which is 100, multiplied by p, or the probability of success at each trial, and that is going to be 0.32. And then we are going to put alpha, and I want to say that I want to be 95% confident that I'm correct. And so what this tells us is that 40, that we can be 95% confident that 40 or less individuals will 40 or less individuals will get accepted into the society. And then last but not least, what is the probability that between x and y gets accepted? Okay, so we do binom dot equals binom dot dist dot range, and then we're going to put the number of observations, which is going to be 100. Oh, there's a space there, that's why it's not popping up. The number of trials, the probability of success at each trial, which is 0.32. And then the lower number, let's see here, let's just put, let's put 30 and then 40. I want to know what's the probability between 30 and 40, and that's going to be 66.5%. And so you can just use this calculator over and over and over again. And if you have the formulas in there, you can actually just update, these things up here. And the way that you could do this is instead of putting 100 right here, you just click on N. Okay, instead of putting 0.32 right here, you put 0.32 right there. Instead of putting 30 up here, you would have to have those numbers off to the side. But by putting in the basically the cell references, you have the ability to move much faster. So that's how you do this. Hopefully this was beneficial with the binomial probability distribution. The binomial probability distribution, like I said, there are two possible outcomes, a success or a failure. And this tool really helps you to understand how to determine the probability, of every single possible success or failure, or every single possible number of success or failures.